Welcome back, everyone. This is Professor Herring. In this video, we're going to continue our discussion on intermolecular forces and look at a particular type of intermolecular force that we call hydrogen bonding. To summarize what we've talked about already, we discussed dipole-dipole forces and London dispersion forces, as well as forces that involve ions. Dipole-dipole forces and London dispersion forces are known collectively as van der Waals forces. And what we see that for these molecules is that if you compare them, I've got here 6 different molecules with similar molar masses, all within a couple AMU or grams per mole of each other, but they're varying based upon their molecular polarity. And what we see is that for differences or rather, when they have similar mass and shape, as do these molecules, the differences in the intermolecular forces are a function of the dipole moment. Higher dipole moment means higher intermolecular forces overall. Well, what about the opposite scenario? What if we have differing molar masses, but also differing polarities? If we take a look at this trend, what we can see is that the dipole moment is actually decreasing as we go from left to right, while the boiling point is increasing. And that's opposite of what we just said. On the previous slide, we said increased polarity should mean increased boiling point. That's when they have the same molar mass. However, these have drastically different molar masses. And what we see is then essentially the molar mass greatly outweighs the dipole moment when it comes to vastly different molar masses. And so what we see here is that if they have vastly different molar mass, then molar mass is the determining factor. However, there's an important exception that we need to pay attention to. If we take a look at hydrogen fluoride, it's in the same family, hydrogen with a halide. It has a much lower molar mass, much higher polarity, and a much higher boiling point. So why is it that even though we have the large discrepancy of molar masses, that this bucks the trend? We're going to talk about the reason for that, and it's due to what we call hydrogen bonding. Now, the term hydrogen bonding, you want to be careful because it's not a covalent bond. In fact, calling it a bond is somewhat of a misnomer. It's really an intermolecular force. However, it's stronger than the other intermolecular forces, specifically the van der Waals forces. So the ones that involve polar or nonpolar molecules, hydrogen bonding is stronger. So if we compare the boiling points of hydrogen compounds in group 4, that's this group right here. Oh, let me do that over again. It's this group here on the bottom. We see that as the molar mass increases, so does the boiling point. However, groups 5, 6, and 7 have an anomaly. And these molecules have much higher boiling points despite their lower molar masses, and that's due to hydrogen bonding. So what is hydrogen bonding? Well, they have a directional component. It's essentially a supercharged polar bond. Interacting with the hydrogen of a different polar bond. And the direction matters. So in order to have a hydrogen bond, you have to have the electrons of a polar oxygen, nitrogen, or fluorine that are lined up with the bond down the bond of a different hydrogen-oxygen or hydrogen-nitrogen, hydrogen-fluorine bond. So this could be hydrogen-nitrogen or hydrogen-fluorine as well. And this must be a polar nitrogen, oxygen, or fluorine with its electrons. Okay? Just to clarify, the hydrogen bonds form between the lone pair, right there, of a partially negative oxygen, nitrogen, or fluorine atom, and the partial positive hydrogen, which itself has a covalent bond to nitrogen, oxygen, or fluorine. Okay, and I'm going to walk you through some examples of this and some non-examples as well. And it turns out that there's other things that can form hydrogen bonds. If you have elements with negative charges, then those can form hydrogen bonds as well. But we're going to restrict our discussion of hydrogen bonding to this main group here. That is the electrons on a negatively charged oxygen, nitrogen, or fluorine interacting with a positively charged hydrogen that has a covalent bond to oxygen, nitrogen, or fluorine. And this is our hydrogen bond. It's very common for students to think that this is the hydrogen bond. So don't fall into that trap. Hydrogen bonding is essential for DNA's base pairing. In fact, it is the reason why the base pairing occurs. Adenine and thymine interact through 2 hydrogen bonds, whereas guanine and cytosine interact with 3 hydrogen bonds. And the shape and the number of hydrogen bonds here is what makes it so that way these base pairs only interact with the bases interact only with the proper pair. In other words, adenine would not interact well with guanine or cytosine because adenine needs to donate 1 hydrogen for a bond and accept a different hydrogen within a bond. Whereas the guanine and the cytosine, they're paired more properly. All right, let's try a practice problem. Which molecules below could form hydrogen bonding with another molecule like itself? This is important, this distinction here, because you can get molecules that can hydrogen bond with other molecules, but not necessarily themselves. So, just to clarify, to form a hydrogen bond, we need an acceptor and a donor. The acceptor is the oxygen, nitrogen, or fluorine with its lone pair, and the donor is the hydrogen that's bound to the oxygen, nitrogen, or fluorine on another molecule. Okay, so let's go through this. A does not have an acceptor. There's not a negatively charged oxygen, nitrogen, or fluorine. This indicates that we have a positively charged nitrogen. However, it does have a hydrogen bound to nitrogen, and that means that it is a donor. So any one of these hydrogens could be donated within a hydrogen bond. B, this has an acceptor. There's a lone pair of electrons on the nitrogen, and this is a polar bond pointing that direction. However, there's no donor. Remember, this right here indicates a carbon because it's at a juncture. And so this hydrogen is covalently bound to carbon, which means that it cannot be donated in a hydrogen bond. So these 2 molecules could interact with each other. You could get the nitrogen interacting with the hydrogen on the molecule on the left, but on their own, they cannot hydrogen bond to themselves. C does have a donor. It has lone pairs of electrons on the oxygen, which has a polar bond. However, there's an acceptor, but there is no donor. Remember, that's a carbon right there. And so we have hydrogens that are bound to carbons, that's not a strong enough polar bond to get an interaction for hydrogen bonding. D does not have an acceptor and does not have a donor. Why is that? There are electrons there, but the bond between the chlorine and the hydrogen, while it's polar, it's not polar enough for it to be classified as a hydrogen, for it to be able to participate in hydrogen bonding. What about this one? This has an acceptor and a donor. If you look at the rules of valence, this nitrogen needs a set of lone pair electrons here, and this is a covalent bond between hydrogen and nitrogen, and so we could get multiple of these molecules lining up and forming that hydrogen bond. So when we're estimating the relative strength of intermolecular forces on different molecules, let's summarize here. If we have nonpolar molecules, but that have the same molar mass in different shapes, the more compact or the lower surface area is going to have fewer dispersion forces. That would look like something like the following. This is a carbon chain with 6 long. Same number of, these are both C6H14, but this is more compact. Therefore, it's going to have fewer dispersion forces. For covalent molecules that have similar molar mass and shape, we're going to look at the dipole moments. The stronger the dipole moment, the stronger the intermolecular force. And this is especially true if one of those molecules can do hydrogen bonding and the other cannot. For molecules that have substantially different molar masses, so if we have something that's vastly different in molar mass, then the higher the molar mass, the higher the intermolecular forces. That's due to those dispersion forces, the induced dipoles. However, ultimately, the most important thing is that if you're given data that gives you melting point or boiling point data, it doesn't matter if you think that one has more dispersion forces or higher polarity or hydrogen bonding or whatnot. The higher the boiling point or melting point, the stronger the intermolecular forces. And I guarantee you that you're going to see some scenarios where it's meant to trip you up and where you just need to follow the actual macroscopic trends of melting point and boiling point. If we have conflicting trends, but we don't have boiling point or melting point data, this is the general way in which you want to apply the intermolecular forces. Generally speaking, hydrogen bonding is the first thing that you should look for and consider. After that, you want to consider the relative molar masses, molecular weights of the molecules. And you want to do that if they're outside of about 10 AMU difference, or 10 grams per mole. So in other words, if we have something that's 95, 97, 99, those are all essentially the same when it comes to London dispersion forces. Okay? After we've considered the molar mass, at that point we want to consider polarity, and then looking at the shape and the surface area. Now, these are the priorities, but there are lots of exceptions to this list. And when those occur, that's when you really need the boiling point or the melting point data. All right, that's it for this video. Thanks for watching. If you have questions, ask on Piazza and office hours or recitation. Have a good day.